Okay, I wanted to complete the problem from Friday's class with the circular pond, making it across the pond in the shortest time possible. And I actually want to kind of start over with a variation on this problem I think is better. And so it says in one part of an outdoor race, competitors come to a circular pond with a radius of 1.8 kilometers. They must make it to the point directly across the pond, the other end of the diameter. So here's where the racers come to here. They need to make it to this point by swimming and or running around the pond's edge, which is rocky and uneven. One racer, Josie, can run 4 kilometers per hour around the edge on the rocks, and she can swim 3 kilometers per hour. How should she choose point P, as shown in the diagram, to complete this part of the race as quickly as possible? So again, the scenario is she's going to start here, and she can choose to run as far as she wants around, and then she can start swimming also from that point. So the point P is variable. So how should she choose the point P to make it directly across the pond as quickly as possible? And so we said with these optimization problems, we're looking for a quantity that can be maximized or minimized, and we want kind of the centerpiece of the whole solution will be the function whose output is that quantity that we want to maximize or minimize. And we talked about if she wants to complete this part of the race as quickly as possible, that the quantity in focus here is the time it takes her to get from start to the destination, and we're trying to minimize that time. So what we're after is a time function. Or the time that it takes Josie to get from the start to the destination. And so the structure of that function is going to look like this. We said this in class. The time it takes her to run to point P, and then the time it takes her to swim from point P to the destination. So we can say T for the run plus T for the swim. So that's going to be the structure of our time function. And to calculate the time she spends running, it's going to be her distance for the run divided by the speed that she can run, and we saw that that's 4 kilometers per hour. And similarly, the time for the swim is going to be the distance for the swim over the speed that she can swim, which is 3. So what quantity then determines this point P? So we need this time function as with a single input quantity. So the single input quantity that would determine exactly where P is. And we saw on Friday that that would be this angle theta. So given this angle theta, that would determine a unique point P that she would run to and then swim from there. Okay, so we want to get this distance that she's run in terms of theta and the distance that she's going to swim in terms of theta. And then we'd have the time. If we have both those in terms of theta, then we'd have a time function in terms of theta. So we'd have it. So let's just do a quick review. If this is angle theta radians, then measuring in terms of the radius, this arc length then is theta radius lengths. Or theta radii. That's where angle measure in radians comes from. It comes from measuring arc length cut off by the rays of the angle in terms of the length of the radius. So if that's theta radians, then that's theta radii. This horizontal distance of point P measured in radii is by definition cosine theta. So if we took the radii of the circle, radius of the circle, and measured this fraction of the radius, this looks like something like 0.75 or 0.7 maybe, that would be cosine theta. And then the vertical distance of this point P on the circle, measured in radii, is sine theta. So this arc length, this horizontal length, this vertical length, measured in the units of the radii are theta, cosine theta, and sine theta. But we want these distances in kilometers. Well, if each radius is 1.8 kilometers, then getting these distances in kilometers is easy, because if we're measuring in radii or radius lengths, then we're just going to take that number of 1.8 kilometers to get how many kilometers that is. So we're going to take that number of 1.8s, and that'll give us kilometers. Similarly, it'll be sine theta times 1.8, and that'll be how many kilometers that is. And similarly, this arc length will be 1.8 times the number of radii that is. Okay, so we have this distance is 1.8 cosine theta, 1.8 sine theta, 1.8 theta. So then her distance run is this 1.8 theta. So now we're ready to write the time function. It is 1.8 theta over 4. Her distance swam, or distance of the swim, is this hypotenuse of this right triangle here. So we could take this whole length squared plus this length squared would equal the swim squared. And so the swim would be the square root of, well, this side is 1.8 plus 1.8 cosine theta, and we would square it. And this would be our sine theta. 1.8 sine theta is the height of that right triangle squared. If we take the square root of that whole thing, that's the length of that hypotenuse and the distance that she swims. At the end of this video, I'm going to show you how to simplify this whole hypotenuse here, so that it becomes 1.8 times the square root of 2 plus 2 cosine theta. And so what's under the radical here, or this whole expression, is the same as 1.8 times 2 plus 2 cosine theta, which, if you want to see that how those are equal by the algebra and trig identities, stay tuned at the end of the video. So we have the centerpiece of this solution, which is our function, whose output is the quantity that we're trying to minimize, the total time for Josie to get from the start to the destination, which is her time spent running plus her time spent swimming. Okay, so then we know that minimums could occur at a local minimum, and a local minimum occurs where this accumulation function pauses. And so pauses are where we want to take the rate of change, the derivative. We're going to set it equal to 0 to get potential local minimums, or values of theta that give us a local minimum. So the derivative here, this is 1.8, would be 1.8 over 4. That's the derivative of that term there. Plus we've got, let's make that 0.6. And it's going to be times, be 1 over 2 times radical 2 plus 2 cosine theta times the derivative of the inside by the chain rule, negative 2 sine theta. So here is our derivative, and we know that when that equals 0, we want to set this equal to 0 to get potential local min. So solving this equals to 0 is another kind of long algebraic process. I'll show you at the end of the video. But from that, we get our critical values. I'm just going to write these down and stick to the kind of the meat and potatoes of the solution and not get lost in the algebra. So critical values turn out to be, theta turns out to be the arc cosine of -1/8, which is a good approximation for that, 1.696 radians. And then also another critical value, theta equals pi. We should really go back here and define in this our function for time a domain. What values of theta make sense here for our situation? So clearly the starting value of theta, the least value of theta that would make sense would be theta equals 0. And that would be if Josie swam straight across the pond. So domain here is going to be 0, less than or equal to theta, knowing that 0 is if she swims the whole way. And then what's the greatest value of theta that makes sense? Okay, so we think about she could run to point P. This is all possible. We could run to point P here. So what's the limiting situation here? Well, she just runs the whole way. So what angle would that be? So right now, theta is actually this angle here. So what angle is her running the whole way around the top of the circle? Well, that would be pi radians. Okay, so that's our domain for this function. The values of all possible values of theta that make sense. And our critical values then, 1.696, we see that that is definitely in the range. Actually, 1.696 is a little bit greater than 1.57, or theta pi over 2. So maybe something like this right here would be this critical value here, 1.696. And then theta equals pi, which we said is her running the whole way, would be the other critical value that you get when you set your derivative equal to 0. Okay, so let's take a look at this critical value here. We want to see if this is local minimum, or could be local max, or could be neither, right? We saw different situations for critical values. And just from the math we've done so far, we don't know what we have. So one way to find out what kind of critical value this is would be to take the second derivative and see if it's positive or negative. If we're looking for local minimum, we know that second derivative needs to be positive, or saying that the rate of change is increasing. If the second derivative is negative at this value, then we'd have a local maximum, because we'd have decreasing rate of change, or concave down. That's one way. Looking at the second derivative is one way to do it. So I'm looking at this function here, and second derivative is looking a little bit like more algebra than I want to do. So another way that we could look at what kind of critical value we have is to just look at whether the first derivative is positive or negative to the right, just to the right and left of this critical value. If we're looking for a local maximum, we're looking for a shape like this. And so we know that if the critical value is right there, actually we're looking for local minimum. So if we're looking for local minimum, what would we have? Something like that. Our critical value, we know, is right there. And so if we're looking for local min, then if we took a theta value a little bit less, we'd expect that first derivative to be negative, because we have a decreasing function. And if we took a value of theta a little bit greater than this, we'd expect the derivative to be positive, indicating an increasing function. So if the function is going from decreasing to increasing, then that's local minimum. We can check that, decreasing to increasing, by looking at values in the first derivative to see if they're indeed negative and then positive. Okay, so we can take, say, 1.6, look at the derivative at 1.6, and then the derivative at, say, 1.8, because we're right about here at 1.7. So let's look at the derivative at 1.6 and the derivative at 1.8. If we were to put 1.6 into our derivative, we would get a value of 0.02, approximately. And if we put the 1.8 into the derivative, we get a value of approximately negative 0.02. So what's happening here? What kind of critical value do we have at 1.696? Well, this would indicate that the function is increasing and then decreasing. So really the situation we have at 1.96 looks like this. Not a minimum as we were expecting, but this is actually a local maximum at this angle of 1.696. Or it's looking like this is the longest for her to run to this point and then swim like this would take the longest amount of time, not the shortest, based on this analysis here. So let's kind of look at what we have so far and make a sketch. So we're looking at our time, say hours here, and our angle theta here. What we found is from 0 to pi, so here's 0, here's pi. At our critical value here, our cosine of negative 1/8 or 1.696, it's actually a local maximum. And since there's no other critical values in that range from 0 to pi, we have that one at pi, but that's at the endpoint. There's no other critical values in between. This thing has to look like this. It has to be going up, hit a maximum, and then go back down again. So based on the math we've done so far, this is what we can conclude, that we have a local maximum at this critical value. And if it's the only critical value, then it's heading up that whole way and then heading down in this range, in this domain from 0 to pi. So if we're looking for the shortest, then the least amount of time must be at one of these endpoints, not at the critical value, but at one of these endpoints. So that means that the critical value then is either at, or sorry, the minimum amount of time that she could run must be at either 0 or pi. Because of the way this graph must be shaped, if that's the only critical value and it's a local max, then it must be rising this whole way and then falling this whole way. Therefore, at 0 or at pi would be the least amount of time she would spend. So let's figure it out. So we can go back to our original function that gives us the time, and we can put in time of 0 and put in time of 1.696. That was our critical value, and put in time of pi and calculate these, and it turns out that if we plug 0 into this, we get 1.2 hours. If we put 1.696, we get 1.56 hours, 557. And if we put pi in, we get 1.414 hours. Which is further evidence here that we have a local maximum. It's backing up what we assumed here with the sketch. And if we look now, we see at an angle of 0, it'll take her 1.2 hours to get to the destination, and with an angle of pi, 1.414 hours. 0, remember we said an angle of 0 means she swims the whole way. Pi, this angle means that she runs the whole way. And so looking at these three values, we see that the local minimum occurs at an angle of 0 with a time of 1.2 hours, all swimming. She should just swim. She should just avoid running at all and just swim straight across. And that will be her least amount of time to complete this part of the race. And so what this shows is that in a given situation, the maximum or the minimum of a function might not necessarily be at the local max or local min at a critical value. In this situation, we saw the critical value gave a max when we wanted a min. And so what we need to do is we need to check the endpoints of our domain and then compare all the possible outputs of the function to see which truly gives the least value, if that's what we're looking for, or the greatest value, if that's what we're looking for. If we were looking for the least value, it would be at the starting value of the domain, which was not a critical point. We did not get 0 for a critical value. And then the maximum time would be at this critical value at the local max of 1.557 hours that it would take to complete that part of the race by choosing that angle. So that's the conclusion that we make, that to this point we've just assumed that a local max or local min gave us the true max or min in a given situation. Well, that's not the whole story. The whole story is that you need to check the endpoints of your domain, because those could possibly be the solution to your problem. Okay, so that solves the problem that she should swim straight across, choose an angle of 0, just swim straight across for a minimum time in this part of the race of 1.2 hours. Now I want to show you how to solve for this expression right here to get the radical 2 plus 2 cosine theta. So I'm going to erase everything here. And we saw that it was the square root of 1.8 plus 1.8 cosine theta squared plus 1.8 sine theta squared. So I want to show how I got that simplified expression that I used in the time function. Okay, so we can expand this. And when you expand this, you get 1.8 squared plus 2 times 1.8 times 1.8 cosine theta plus 1.8 cosine theta squared. And that was plus 1.8 sine theta squared. I'm just going to write s theta for room here, meaning that's sine theta. And that's all under the square root. Okay, and what we notice here is there's a 1.8 squared in every single term. 1.8 squared, 1.8 squared, 1.8 squared, 1.8 squared. So that can be factored out, and then, well, let's do that. 1.8 squared. And then I'll have 1 plus 2 cosine theta plus cosine squared theta plus sine squared theta. Again, all under the radical. Because these are multiplied, I can apply the square root of the first times the square root of the second. You cannot do that when you're adding and subtracting terms under a radical. But since these are multiplied, the square root of a product is the product of the square roots. So the square root of 1.8 squared is simply 1.8. And now I have the square root of this right here, cosine squared plus sine squared. If you remember, in radius lengths, That's cosine theta. And this is sine theta, measured in radius lengths. And measured in radius lengths right there, that is 1. It's 1 radius length. So by the Pythagorean theorem, cosine squared plus sine squared equals 1 squared. So therefore, this equals 1 squared right here, because this would be a squared plus b squared. So, and 1 squared is just 1. So this whole thing is 1. And 1 plus 1 is 2. Plus 2 cosine theta. And that was the expression that I used in the time function. So this right here is equal to this. And this is what I used in that time function. Okay, the next thing I need to do is show you how I solved that, the derivative equal to 0 for theta to get those critical values. So I'm going to erase here. And we had the derivative was, so we had found the derivative was 1.8 over 4 plus 0.6 negative 2 sine theta over 2 times square root of 2 plus 2 cosine theta. And to get critical values, we set that equal to 0. Okay, the first thing I want to do is I'm going to go ahead and take 2 over 2, which is 1, so those go away. And now I'm going to move this over to this side, setting these fractions equal. I'm going to add this resulting fraction to both sides. And so what I'll get is 0.6 over square root of, or 0.6 sine theta, I should say, 2 plus 2 cosine theta. And that's going to be equal to 1.8 over 4. Okay, and then to get rid of these fractions, let's cross multiply. 2.4 sine theta equals 1.8 times this radical expression. Okay, and then let's make our numbers a little easier here. Notice that this 2.4 is actually, oh no, 1.8, that's true. Okay, so let's just, let's multiply by 10. Okay, we're going to multiply by 10, and I want to do that, multiply by 10, and divide by 6. We multiply by 10 and divide by 6, we'll have 24 and 18, and then we'll have 4 and 3. So this really becomes 4 sine theta equals 3 radical, the same radical that's here. Okay, we buy that. This is, 2.4 is 4/3 of 1.8. So we can say this is 4 and this is 3. Or you can multiply by 10 and divide by 6. Okay, so now I want to get rid of this square root. I'm going to square both sides. So I'm going to have 16 sine squared theta equals 9 times 2 plus 2 cosine theta. Squaring what's under the square root just gives, squaring that square root just gives what's underneath. Okay, so now I've got a quadratic of sine here. So it would be nice if this was all in the same, either sine or cosine. So going back to this, it's cosine theta and sine theta, and 1. Cosine squared plus sine squared equals 1. So therefore, sine squared equals 1 minus cosine squared. So by substituting in 1 minus cosine squared, I get a quadratic of cosine. So 2. And I'll go ahead and multiply this out. 18 plus 18 cosine theta. Okay, so with quadratics, we move everything to the left and get a 0 on the right. So I'll have negative 16 cosine squared minus 18 cosine. And then I'm going to have 16 minus 18, so minus 2. Make sure that I've got the right thing here. Yes, I do. Okay, minus 2 equals 0. And then I want to divide by negative 2. So I get 8 cosine squared theta plus 9 cosine theta plus 1. Okay, and so this is, I'll do it in blue, this is basically the same as 8x squared plus 9x plus 1, where I just said x equals cosine theta. And so this factors as 8x plus 1 and x plus 1. So then x is negative 1/8 or negative 1. But what was x? X was cosine theta. So cosine theta equals negative 1/8 or negative 1. And so theta is the arc cosine of negative 1/8 or arc cosine of negative 1. Or what angle of theta gives negative 1? Well, negative 1 would be the angle that puts you here on the circle, and that would be our angle of pi. So the other one would be pi. So what angle theta gives a cosine of negative 1? Cosine of negative 1 means you're here, so it'd be this angle theta swept all the way around like this. Will give a cosine of negative 1. And that's theta equals pi. So that's how I got those critical values by setting the derivative equal to 0. That's the solving process that I went through to get those critical values of arc cosine negative 1/8 and pi. Okay, that does it for this problem. If you have any questions, don't hesitate to ask.